Welcome to the lectures for Class 6 in our Artificial Intelligence course, and this is going to cover Russell and Norvig, our main text, up to the point in the text where it starts talking about resolution. I'm going to talk about resolution, but you don't need to read the chapter part on resolution after that unless you're really interested in it. I'm mainly interested in how resolution works and what it's good for, as opposed to proving that resolution works. So here's what we're going to talk about. We'll talk about showing that first order inference is sound because we can transform first order inference to propositional inference, which we know is sound. I'll talk about unification, which is how we bind variables to values. I'll talk about generalized modus ponens, which is a way of showing that the kinds of syllogism reasoning we did using propositional logic will also work for first order logic. Especially important, we'll talk about forward and backward chaining. We know about those already, but we'll take a little deeper look. We'll connect what we're doing with logic to logic programming, namely Prolog, sort of bringing together the two big threads we've seen in the class so far. And we'll talk about resolution and connect resolution to Prolog as well. So here goes. So logic, and the first order logic which we're using, fits into a long history of logic, but as we'll see, most of the logic that we really are using is from the last 100 years or so. And we begin with ancient Greece and the Stoics, who basically had propositional logic, maybe inference. It's a matter of some debate because the records for the Stoics are not that good. Aristotle, the root of all science and logic, gave us the idea of syllogisms. And although the names modus ponens and modus tollens are Latin, he came up with the basic ideas and had the idea of inference rules. Cardano, in the Renaissance, came up with the idea of probability theory, which basically combined propositional logic with uncertainty, and that's actually a field which is active today. Boole independently reinvented propositional logic, and that's why we talk about Boolean variables, right? Because they're either true or false. And Frege then, shortly thereafter, developed first order logic, which we've been studying for the last couple days. Wittgenstein, among other things, showed how to do proof using truth tables, and we've seen truth tables a little bit in our class. For instance, when we showed an alternate way of representing implication. Gödel showed that there exists a complete algorithm for first order logic. That is, you can, given a set of propositions, find a proof. Herbrand showed also a complete algorithm for, well, in other words, Gödel showed that such a thing had to exist, but he didn't give it to us. Herbrand gave us one basically by showing that you could reduce first order logic to propositional logic. Gödel, a little later, showed that there was no complete algorithm for arithmetic, and which of course makes mathematics interesting. Much later, Davis and Putnam created a practical algorithm for propositional logic. In other words, what Herbrand did was true in theory, as we'll see, but it doesn't really work very well when we have variables that can take on many values. And finally, in 1965, Robinson came up with a practical algorithm for first order logic, namely resolution, and we'll be looking at resolution. So before we get into the rest of the chapter, I want to take a little bit of a side trip to look at resolution. So suppose we know that P is true or Q is true, and suppose we know also that P is false or R is true. Now, let's think about this. If P is false, then by the first clause, Q must be true, right? If P is true, then Q is true. But if P is false, which should be here, then by the second clause, R must be true, right? So either P is true or P is false, which means either Q is true or R is true. So that's why we have this representation. So we say P or Q and not P or R means that we can conclude Q or R. Now, here's that same thing, but if we think about it, that's exactly the example we had with the unicorn example a few days ago. So remember that one? It was something like, if unicorns are mythical, then unicorns are immortal. And also, if unicorns are not mythical, then they're mammals. I've simplified a little bit, but that's basically what they said. And from that, we can conclude via resolution that a unicorn must either be immortal or it's a mammal. And that's the resolution step. Now, we remember, as I mentioned just a minute ago, we had other ways of expressing implication. So we know that P implies Q is logically the same as not P or Q. So let me rewrite this little inference. Instead of using deduction, instead of using inference, using this OR notation. So exactly the same thing. I now have not mythical or immortal and mythical or mammal implies, from that we can conclude the unicorn is immortal or it's a mammal. Okay? And this notation is actually going to be useful for us, because we can kind of see how the not mythical and the mythical cancel each other out, leaving us the immortal and mammal. So let's try to connect this to prologue. There are lots of different ways of expressing resolution, not just the one we saw. And there are there's like, I don't know, a dozen or so possible resolution steps we could take. And the one I showed you was easy to understand. Here's another one, also easy. So it's basically the same as before, except I've got P or Q and not P or nothing. In other words, I've got P or Q and not P is the same as not P or nothing, right? So I can conclude, based on what we did before, that, look, either P is true, right, in which case Q is true, or P is false, in which case nothing. So I've got basically Q or nothing, which reduces to Q. So that's the same as not P implies Q, that's the same as not P implies Q and not P. Well, right, because P or Q is the same as not P implies Q, right? And so I've got not P implies Q and not P. Well, that's just an ordinary modus ponens syllogism, and I get out Q. So that makes sense, right? So that's a resolution step, a little simplified, where I don't have an OR for this side of this part of this clause. But that's how prologue works. So let's take a look. So here's the same thing as basically not P implies Q. P implies Q, right? Now, and then I've got P as a fact, all right? So the way this works is that if I try to prove Q, okay, it's going to try to prove P, right? Now, the Q we can think of as being a positive Q, in other words, it's true. And if it's on the right-hand side, we think of it as not being true yet, or not. The two P's cancel out, in a sense. I'll have not P, because it's on the right-hand side, and P, which leaves us Q. So basically, what Prolog does in its reasoning is exactly resolution, and it just repeatedly resolves until we basically get nothing, in which case we know it's true. So this is the P that's on the right-hand side, and we can think of it as being not P. It cancels with the P that's a positive literal, and from that we can conclude Q. Here we're going to start approaching unification, and I need to approach that through the notion of instantiation. So we're going to look at two kinds of instantiation, and we'll start with universal instantiation. So every instantiation of a universally qualified sentence is entailed by it. What that means is that if I have a universally quantified variable like v in some sentence alpha, it means that no matter what I substitute for v, any ground term, alpha will be true. So for any variable v in alpha and any ground term, alpha will be true, right? So it basically means that if a variable is universally quantified, right, then no matter what value we put in there, the sentence containing that variable will be true. So for example, if I have for all x, king x and greedy x implies evil x, all right, then no matter what I put as x, it's always going to be true. So as long as it's a ground term. So King John and greedy John implies evil John. King Richard and greedy Richard implies evil Richard. Or any other ground term, like king of the father of John and greedy of the father of John implies evil of the father of John. So that's universal instantiation. Its counterpart is existential instantiation. So here we're saying that for any sentence alpha and some variable v and a constant symbol k that does not appear anywhere else in the knowledge base. So if we've got a constant Richard, k is not going to be Richard. Our idea is that if we say there exists a v for sentence alpha, then it is true that there exists some k that which we can substitute for v that makes alpha true. So for example, if there exists some x so that x is a crown and on head x of John yields crown of C1 and on head C1 John, provided that C1 is some new constant. Now, we don't know a particular crown, but we know that if this is true, it exists. And this made-up constant, C1, is called a Skolem constant. And it's just a technical term, and it means that when we have, it's a constant that doesn't appear anywhere else in the knowledge base, and it's basically an arbitrary constant which we're inventing. So universal instantiation, when we apply it over and over again, adds new sentences to the knowledge base, because if it's true that greedy x implies evil x, then we can add greedy John implies evil John, and greedy Richard implies evil John, and so forth, to add new sentences to the database. And it's logically equivalent because we're just showing basically instantiations of that one inference. Existential instantiation can be applied once to replace the existential sentence. And that new knowledge base is not equivalent to the old knowledge base, but it's still satisfiable if and only if the old knowledge base was satisfiable. So if I have there exists an X such that crown X and on head X John, I apply existential instantiation to posit a constant crown X variable C1. Clearly, and I substitute crown C1 and on head C1 John. Clearly, the knowledge base isn't the same because I don't have for all X crown X and so forth. I have crown C1, but it's still satisfiable if the old knowledge base was satisfiable. Now, let's with these ideas turn to the notion of reducing first-order logic, first-order inference to propositional inference, because we know already that propositional inference is sound, and if we can show an equivalence between first-order inference, first-order logic inference, and propositional inference, then we'll know that inference in first-order logic is sound. So let's suppose the knowledge base contains just the following. For all X, king of X and greedy X implies evil X. King John, greedy John, and brother Richard John. Okay? So if we instantiate this universal sentence in all possible ways, because we only have these ground terms John and Richard, okay, then we have the following clauses. We have King John and greedy John equals evil John, where X is equal to John, and our only other ground term is Richard, so we get King Richard and greedy Richard implies evil Richard, and the others remain the same. So now, effectively, what we've done is propositionalized the knowledge base. In other words, it's exactly equivalent to the knowledge base above, because these are the only conclusions that we can draw from this, and taking out the universal sentence and replacing it with all its possible instantiations, we have a completely instantiated knowledge base, all ground terms, that's equivalent logically to the knowledge base with the universal quantifier. And that is what we call propositionalizing a knowledge base. So our proposition symbols are King John, greedy John, evil John, and so forth. And so there are no more variables left. It's nothing but a set of propositions, and we know that we can apply propositional inference to that. So here's our claim. A ground sentence is entailed by a new knowledge base if and only if it's entailed by the original knowledge base. And a ground sentence, that's the asterisk there, means that it's a sentence that has only ground terms, no variables in it. And now we can claim that every first-order logic knowledge base can be propositionalized so as to preserve its entailments. So our idea is we propositionalize the knowledge base and query it, and we apply resolution like we saw before, and return the result. Now, the problem is that with the function symbols, there are infinitely many ground terms. So if we have father of, right, we can have the father of John, the father of the father of John, and the father of the father of John. And so the problem is that propositionalizing becomes really tough because we'd have an infinite number of ways of making ground versions of our universally quantified sentences. So Herbrand's theorem from 1930 says that if a sentence alpha is entailed by a first-order knowledge base, it is entailed by a finite subset of the propositional knowledge base. So here's the idea. For n from 0 to infinity, we create a propositional knowledge base by instantiating with depth n terms. So if depth 0 would be basically father of John. Depth 1 would be father of the father of John. Depth 2, father of the father of John, and so forth. Okay? Now, and each time we see that alpha is entailed by this knowledge space. And basically, there's a kind of recursive proof that this works. Now, that this is true. Now, the problem is that this proof works if, in fact, alpha is entailed by the knowledge base. But if alpha is not entailed, it loops. In other words, you can, if alpha is true, you can prove that that if a sentence alpha is entailed by a first-order knowledge base, it's entailed by a finite subset of the propositional knowledge base, if, in fact, alpha is entailed. But unfortunately, if it's not entailed, the proof may not terminate. And in fact, there's a very famous result from Turing and Church that says that entailment in first-order logic is semi-decidable. What does that mean? Well, it means that there are algorithms that say yes. In other words, say it's that the reduction, that the propositionalization will work for every entailed sentence, but there is no algorithm that says no to every non-entailed sentence. And interestingly enough, there's a kind of counterpart to this in Prolog. If something is true in Prolog, then we can prove it, but if it's not true, it may loop. So, problems with propositionalization. Okay, so one of the problems is that it seems to generate a lot of irrelevant sentences because we have to create new sentences, ground sentences, with every possible version of grounding. So we've got, so from, for all x, king x and greedy x implies evil x, and we've got King John, and for all y, greedy y, and brother Richard John, it's obvious that we can get evil John, but propositionalization produces lots of facts such as greedy Richard that are irrelevant to proving that. And if we have some number p k-ary predicates, in other words, each predicate has k arguments and n constant, then we're going to have p times n to the k instantiations. And then if we have function symbols like father, father of, and so forth, it gets much, much worse. And I know that much is spelled much, but you know what I mean. So now we can start to get to unification. So if we can get that inference immediately without having to go through all that, if we can find some substitution theta such that king x and greedy x match king John and greedy y, right? Because if we can substitute, if we have a substitution theta such that we substitute John for x and John for y, then that works. And so in general, we can say we can unify alpha and beta with theta if the sentence alpha, if the unification theta in alpha is the same as the unification of theta in beta. Let's try working through some examples. So the first example we'll have is where P is knows John X and knows John Jane. And the question is there a substitution theta that will allow these to be unified? And I think it's pretty clear that John will match with John, and we can match up Jane with X. So sure enough, there's a substitution Jane for X that works. So we can unify those, and theta is Jane for X. How about knows John X, knows Y OJ? Now thinking about it, it looks pretty much like this is going to work, right? Because we can match John against the variable y, and y can take on the value John. And the only other variable we have is x, and it can be bound to oj. And sure enough, here our substitution theta is going to be substituting oj for x and binding y to John. That works. How about knows John x and knows y mother of y? A little trickier. Well, the first part's easy, right? Because we know that we can bind y to John. And now it looks like we're going to have to bind x to mother of y. But that's a problem because we've bound y to mother of y, and if we but that's not so bad, right? Because y has been bound to John. So we'll say, so our substitution theta is we bind y to John, and we bind x to mother of John because mother of y is going to be mother of John. How about this last example? Knows John x and knows x oj. All right, so if we bind x to John, it also means we're going to have to bind x to oj. And that won't work because John and oj are two different ground terms. So that unification will fail. There is no substitution theta that can unify those two sentences. Here we're going to be looking at the soundness of the logic underlying resolution. Now, resolution, as we've seen, depends effectively on the soundness of modus ponens, and we know modus ponens works for propositional logic. The problem we have is that we don't yet know that modus ponens works for first-order logic. So here we'll introduce what we'll call a generalized modus ponens. It's not just the specific modus ponens of a specific set of propositions, but rather modus ponens generalized to sentences that have variables in them. So here's what I mean. Let's say we have a set of sentences or clauses, P1 prime, P2 prime, and so forth, where we've applied a substitution theta to either make the terms directly ground or to produce a binding that will effectively make them ground. And we have an implication in first-order logic with the corresponding clauses P1, P2, and so forth, where they still might have uninstantiated variables. And those clauses imply some ground term Q. Well, if that's the case, we can conclude Q with binding theta, or substitution theta. So, for example, if we know that our substituted clause P1 prime, King John, corresponds to the uninstantiated clause P1 King of X. So John is King John is totally a ground term, and King X clearly has a variable in it, so it's not yet ground. And let's say that P2 prime is greedy Y, and we'll allow the variable Y here because we're going to bind it in a second. And P2 is greedy X. Now so basically we're going to bind Y to X, and we'll know obviously that because X it's the same substitution for the whole set of clauses, so X is going to be John, and therefore Y will be John as well. Okay, so that means that theta is a substitution where X is John and Y is John, and Q will be evil X, and therefore because we apply the substitution theta to Q, we know evil John. So generalized modus ponens works with a knowledge base of definite clauses, by which I mean they have exactly one positive literal. Where have we seen that before? Well, that's exactly the structure of a prologue clause, where we have one clause on the left-hand side, that's called our positive literal, and we have 0 or more clauses on the right-hand side, and we'll call those the negative literals in the sense that we saw when we did resolution that effectively those clauses are considered negated for the purposes of resolution. And we assume that all variables are universally quantified. So that's generalized modus ponens. Let's see if it really works. So basically, we'll need to show that these given these ground clauses P1 prime through Pn prime, and the implication that the uninstantiated clauses P1 through Pn all imply Q entails Q with substitution theta, provided that we have the same substitution for all these clauses for all I. So we start with the lemma that for any definite clause P, we have P entails P with substitution theta, and that's easy because we just use universal instantiation. Okay, now we know also here at number 1 that if we have the uninstantiated implication P1 and P blah 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 through Pn all imply Q, taken together imply Q, entails P1 and P through Pn implies Q with substitution theta, which we know by universal instantiation. That's the same as saying that P1 with substitution theta and P2 with substitution theta and so forth all imply Q with substitution theta. Now, we also know that P1 through Pn grounded entails P1 and through Pn, and that entails P1 with substitution theta and through Pn with substitution theta. Now, if that's true, which it is, this little part here, this is exactly the left-hand side of this implication. And therefore, by ordinary modus ponens, because all these terms are ground, we know that P1 with substitution theta, etc., all imply Q with substitution theta. Therefore, generalized modus ponens is sound. Now, with that, we can start to look again at resolution in a slightly more technical way. So, when we look at a resolution in first-order logic as opposed to just propositional logic, basically we have a set of clauses L1 or L2 through LK, and M1 or M2 through Mn, and from that, generalized modus ponens says that we can infer that L1 or Li-1, etc., all the way through with substitution theta, where basically we unify L1 with not Mj as substitution theta. So that's a little abstract, I know, but let's take a look at an example, and I hope that'll make it more real. So let's say we have the following clauses: not rich X or unhappy X. Now, we know that not rich, just for intuition purposes, we know that not rich X or unhappy X could also be expressed as in implications, so that not rich or unhappy is the same as rich implies unhappy. Okay, so we have not rich X or unhappy X and rich Ken, and by resolution in first order logic we get unhappy Ken. Basically it's like modus ponens but lifted to first order logic. And that's true where we have the substitution theta Ken for X. And what we do if we apply the steps of resolution to a knowledge base in what's called conjunctive normal form, and combined with the negation of what we want to prove, some sentence alpha, and that resolves, then effectively we proved alpha. So going back to our example about Ken here, let's say our knowledge base is consists of the implications in here, and we want to prove that Ken is unhappy. We'll put not unhappy Ken and try to resolve. Now this turns out to be complete for first order logic. In other words, if it's true, we'll be able to prove it. The two sort of main concepts I need to take you to take out of this section is that is that of forward and backward chaining. Now we've seen these already, and I want to show how forward and backward chaining work in first order logic just like they did in propositional logic, except that propositional logic is going to use modus ponens, that is propositional logic without variables, and first order logic is going to use our generalized modus ponens, that is with variables. So in the book there's the example about the Americans who sells weapons and so forth, and let's go through that and take a look first at the knowledge base in logical notation using first order logic, and then we'll go work through them both in forward chaining and backward chaining. So we've got the statement in our example that it is a crime for an American to sell weapons to hostile nations. So that we can express as the following first order logic expression. So if X is an American and Y is a weapon, and X, the American, sells a weapon to Z, and Z is a hostile nation, let's say, then we can conclude that X is a criminal. Right? So next we need to represent the sentence that the country of no-no has some missiles. So in other words, there exists some X such that no-no owns X and X is a missile. So we'll express that as two separate positive literals, or positive clauses. So we'll have owns no-no M1, which is some skolemized constant. We don't know what missile it is. It's just like the crown in the earlier example. And M1 is a missile. And because we have the Skolem constant M1, we know that M1 is a missile, and that's the missile that no-no owns. We just don't know which missile it is, but we know it exists. Next, we need to represent that all of no-no's missiles were sold to it by Colonel West, and that looks like for all X such that X is a missile and no-no owns that missile, then that means that Colonel West sold whatever missile it was to the country of no-no. The next thing we need to represent is that missiles are weapons. So that's an easy implication. If X is a missile, then it's a weapon. Then we will represent that an enemy of America counts as hostile, and that's easy too. We'll say enemy, if X is an enemy of America, then X is hostile. And then in the text example, it says, West, who is an American, which we'll take as meaning basically that West is an American, so that's easy. We can just say American West. And finally, we need to express the notion that no is an enemy of America. So here is that's easy. Now, given that, let's take a look at how we would forward chain to try to conclude that Colonel West is a criminal. So here are the clauses we know to be true, the ones that don't involve implication and we'll use as the base of implication. So we know that West is an American. We know that our skolemized M1 is a missile. We know that no owns N1, and we know that no is an enemy of America. So given the implications which we developed in the previous little section, we can conclude that from these, working forward, that because M1 is a missile, M1 is a weapon, we can conclude that Colonel West has sold M1 to No, and we conclude that because No is an enemy of America, that No is hostile. So now we have these three additional facts, M1 is a weapon, and so forth, and we'll look at, next we'll apply the implications that have these as the conditions in the implications and see what we can conclude from that. Well, the one we have left is basically says that we takes American West and the others and concludes that West is a criminal. Let's take a look at that. We had if you're an American and you had and Y is a weapon and sells XYZ and hostile Z all imply criminal X, and that's exactly what we have. Now, the good news about forward chaining is that it's sound and complete for first-order definite clauses. We're not going to go through the proof for that, but it's similar to the proof of soundness and completeness in what we had for propositional logic. Data log is a kind of knowledge base that has just first-order definite clauses and no functions. So, for instance, it might be a database of crimes that were committed or something, knowledge base of crimes that were committed. And we know that forward chaining terminates in data log in some number of iterations, and in polynomial time, with at most generating at most p times n to the k literals. So that's the good news. The bad news is, as we saw about semi-decidable logics, forward chaining may not terminate if the sentence alpha isn't entailed by the knowledge base. And that's the unavoidable problem because entailment with definite clauses is semi-decidable. In terms of the efficiency of forward chaining, we basically don't need to match a rule on some iteration k if a premise of that rule wasn't added on at iteration k minus 1. In other words, we want to keep going forward instead of starting over all the time. So we'll match each rule whose premise contains a newly added literal. Now, the business of matching can be expensive because you have to do a lot of comparisons. The good news there, though, is that we can basically index the database, and it allows constant time retrieval of known facts. So missile X retrieves missile M1 and so forth, because we've when we've added the fact, we can basically link up missile X with its instantiations. On the other hand, matching conjunctive premises against known facts is NP-hard, and forward chaining is widely used in what are called deductive databases. Let's turn now to backward chaining. So in backward chaining, we start with our premise, and we try to go backwards through the implications, like prologue does, where we start with what we want to conclude and see what we need to prove in order to conclude it. So here, we need to, our goal is to conclude that Colonel West is a criminal, and so we'll start out by looking for the implication that has Colonel West is a criminal as its conclusion. And you'll remember that we have this implication, and that's the one which will match criminal X with our thing we want to prove, criminal West, with the substitution theta West for criminal. So that's where we're going to start, and sure enough, with the substitution theta West for X, we now need to prove the conditions of that implication, namely that West is an American, that Y is a weapon, that sells West M1Z, and hostile no-no. Okay, so proving West is an American is easy because that's a ground clause in our knowledge base. For weapon Y, we have an implication that Y is a weapon if Y is a missile, and we know that M1 is a missile, so that's easy. And we then look at trying to prove sells West M1Z, and with the substitution Z, no for Z, we can do that if M1 is a missile, and that's true, and owns no M1, which we will find out is true in a minute. We'll just have to prove it. So sure enough, we know that M1 is a missile, and we know that owns no M1 because those are ground clauses. Finally, we need to prove that no is hostile, and we have an implication that you're hostile if no is an enemy of America, and that's a fact that we know. Now, therefore, all of the premises that are needed to draw a conclusion are ground truths, and we can conclude through backward chaining that Colonel West is a criminal. So, the properties of backward chaining are that depth-first recursive proof has a space that is linear in the size of the proof, which is really good. Because remember that forward chaining could generate lots of unneeded conclusions that weren't going to be used. On the other hand, it's also incomplete because it could get into infinite loops. So what we'll do is fix that by checking the current goal against every goal on our goal stack, and if the goal is already in the stack, we won't try to prove it again. In other words, we know it's something we're already trying to prove, so we're not going to get into a loop by trying to prove it again. Backward chaining can also be inefficient due to repeated proving of the same subgoal. In other words, proving the same subgoal may be needed to prove multiple conclusions, or disprove multiple conclusions for that matter. So instead of having to prove the same thing over and over again, we'll fix that by caching previous results. Now, that uses some extra space, but it saves us a lot of time. This backward chaining is widely used in logic programming, but Prolog, at least as we have it, and basically all Prologs, don't check the current goal against every goal in the stack, and they don't cache previous results. So when you're writing your Prolog program, you're going to have to be careful to avoid situations that are going to throw you into infinite loops and you might have to worry about the order in which you prove things to do that. And you also might want to think about your program's efficiency so you don't have to keep proving the same thing over and over again. So as we know, Prolog is a programming language that tries to produce a running version of first-order logic. So as we know, it uses backward chaining with horn clauses. That is, it has at most one positive, literal and 0 or more negative literals, and plus some stuff like arithmetic. It's widely used in Europe and Japan. It was the basis of a very famous artificial intelligence initiative called the Fifth Generation Project, and it's very efficient. Compilation techniques let us approach something like 1 billion logical inferences per second. So it can be very fast, and in fact, Prolog is the logical engine behind the inference in IBM's highly successful Watson program, which beat, or system I should call it because it's rather complex, which beat humans playing Jeopardy. So it's very much an active tool and one of the main active tools in the tool chest for people doing real artificial intelligence today. So what's a program? Well, a program is a set of clauses where each clause is a head, at least one head, and followed by 0 or more literals, which are negative literals. And so if we have just the head with nothing on the right-hand side there, that's a fact that's known. And if we have a head with 1 or more literals, then we know we have an implication. So for example, we express our example we just did as criminal X if American X, weapon Y, sells XYZ, and hostile Z. So Prolog turns out to be pretty efficient because instead of interpreting everything from scratch, they basically do a kind of compilation where they directly link the terms to each other so they know what's going to match. It uses depth first, left to right backward chaining. It's got built-in predicates for arithmetic, as we've seen. So we know to use is for arithmetic rather than equals, which is a test. And it uses something called the closed world assumption. That is, it means if we can't prove it, then we believe it's false. So for instance, if we have alive X, if not dead X, then if there is no fact in the database, dead Joe, then alive Joe should succeed. So in this lecture, we've been able to tie together the logical formalism of first-order logic and the implemented programming language Prolog, and see how Prolog relies on resolution and first-order logic to run, and it does so using backward chaining. And with that, I'll see you in class.